So without further ado, here it is, the mean value theorem, or the MVT, the mean value theorem for derivatives. It's in your book in chapter 4 on page 196. What it says is, if f of x is continuous on the closed interval and differentiable on the open interval from a to b, then there's a point C in AB where f prime of C is equal to f of b minus f of a over b minus a. That is to say, the instantaneous rate of change is equal to the average rate of change. All right? Like any theorem, this theorem has hypotheses and a conclusion. We're going to talk a lot about hypotheses and conclusions since this makes, I think, about our third major theorem in a little bit. All right, so look for the if and the then. You must meet both of the criteria in order for the theorem to apply. All right, in this case, the criteria are a little complex, so the AP exam loves to find ways to make sure you know it. That in order to use the mean value theorem, that f has to be continuous on the closed interval and differentiable on the open interval. So our problem when we did this function y equals x to the 2/3 power is that this non-differentiable point, it's not just that the non-differentiable point was in the interval, it was in the interior of the interval. So my original interval was -1 to 1. So here's what I mean about the difference between the interior and the end point of the interval. What if we look for a point on the same function, but in this time we're going to change the interval to just be 0 to 1. So we're including the 0. Right? This is a closed interval, so we're including the 0 and the 1. We know the non-differentiable point is at x equals 0. But since it's on the borderline, since it's on the end point of the interval, all right, that means that the function is still differentiable on the open interval because the endpoint a is not included in the open interval. So if we had a discontinuity on either of the endpoints, then the MVT would not apply because of the first criteria. But we can have a non-differentiable point on one of the endpoints because the endpoints are excluded from the differentiability criterion. By the way, singular criterion, plural criteria. That's an English lesson for you today. People misuse this all the time. Singular criterion and plural criteria. So you can say, have I met the criteria to be on the sports team? And the coach, being a smart alecky coach, says, there is but one criterion to be on this team. You have to be a winner. All right, he's a coach that, he's a little, he doesn't care about the rules. He just wants to win. Sound like anybody you know? I don't know. Could be people you know. They say cheaters never prosper, but sometimes they do. All right, anyway, so if this mean value theorem applies when there's a non-differentiable point on the end point of the interval, then we should be able to find such a point for x to the 2/3 power on the closed interval 0 to 1, because now the non-differentiable point is on the end point of the interval, not in the interior of the interval. All right, well, let's try it. So we need to solve f prime of c. This is what you're always going to do when you try to find these mean value theorem points. That's sometimes, what is the point guaranteed by the mean value theorem? So that's what we get when we solve this. So my equation is 2/3 c to the -1/3 equals, okay, not too hard to figure out that f of b is 1, and f of a is 0, and then it was 1 minus 0 for a and b as well. So that equals 1. So I'm solving 2 over 3 cube root of c is equal to 1. All right. So that means, like how are you going to solve this? So we could get, for example, 2/3 equals cube root of c by multiplying both sides by cube root of c. That's assuming, by the way, that c is not 0. And here's how I know that the c is not 0. Because the point c is in the open interval ab, therefore it can't be equal to the endpoint, which is 0. Therefore, I can multiply both sides of the equation here by cube root of c, because I know the c is not 0. All right, so if 2/3 is the cube root of c, then I can cube both sides and find out that 8/27 is equal to c. All right, so that's my point. There is a point. Let's see what it looks like. So here's the same function. I've changed my zoom a little bit so I can see the interval from 0 to 1 right there. So we're going from here to here for our secant. Let's go ahead and put that secant on there. there's the secant line, from 0, 0 to 1, 1. All right, from 0 to 1 on this graph, there's our secant line. And so once you know that the coordinates of the point are 8/27 and the slope is 1, we can easily get the equation of the tangent. I found the equation of the tangent here, and there it is. So we can see that nice tangent line that is parallel to the secant line at the point. That point is supposed to be 8/27. Here, let me flip over on me. This is supposed to be 8/27 right there. 0.2963, is that 8/27? Sure it is. All right, so next we will look at some more. Well, let's find another one of these points. I guess, yeah, sure. This is a little too similar to what I had there, but let's go for it anyway. I've got f of x equals x to the 2/3 power on the interval 0 to 4. Is there a point where f prime of c equals f of b minus f of a over b minus a? If so, find it. Well, first of all, what do you think? Is there such a point? Okay, answer yes, because although there is a non-differentiable point at x equals 0, that is not included in the interval. That, by the way, is something that we would want to state here. So there is such a point. And we might say, although f has a non-differentiable point at x equals 0, 0 is not in the open interval from 0 to 4. So f is differentiable on the open interval 0 to 4 and continuous on the closed interval 0 to 4. Therefore, the mean value theorem applies. So this is what we want to say in order to consider that endpoint, that non-differentiable endpoint, and yet make the correct conclusion that the MVT applies by appealing to both of the hypotheses and then stating that it applies. Next, we will apply the conclusion of the mean value theorem to find the point.